In 1903, the Nobel Committee awarded physics highest honor for a discovery that appeared to violate physics itself. And the woman who shared that stage in Stockholm had proven something that unsettled the foundations of science. Matter destroys itself, and atoms, those eternal, indivisible building blocks that had defined chemistry for 2,000 years, were dying silently and continuously in the uranium beneath your feet, in the potassium, in your bones, in the walls of this room, and nothing in the universe can stop it. You believe matter is solid, permanent, and unchanging, and you would swear that the metal in your hand today will remain the same metal tomorrow, next year, and 1,000 years from now. That assumption is wrong. Right now, that metal is transforming, not through chemistry, not through heat or pressure or any force you can apply, but from within the atom itself. Once I understood what this meant, I realized we had been deceived by the most basic assumption in all of science. For 2 millennia, atoms were considered eternal, and the word itself, atomos, is Greek for that which cannot be cut. This was bedrock truth, the atom as the smallest thing, the final thing, the permanent thing, and entire sciences were built on this foundation. Then, in a leaking shed in Paris, I watched that foundation crack. What I am about to tell you will transform how you see every piece of matter around you, because once you understand what is truly happening inside the atom, you will grasp a truth I carried with me to my grave. Stability can only be attained by inactive matter, and nothing in this universe is truly inactive. This revolution began not with triumph, but with failure. In 1896, the physicist Henri Becquerel was trying to prove a hypothesis about uranium and fluorescence, believing that uranium salts exposed to sunlight would emit X-rays, those mysterious rays Wilhelm Röntgen had just discovered. Becquerel prepared his experiment carefully, placing uranium salts on photographic plates wrapped in black paper, ready to capture any rays the fluorescence might produce. Gray clouds settled over Paris for days, and without sunlight his experiment could not proceed. Frustration led him to develop his control plates anyway, expecting to see nothing. But the plates were fogged. Somehow, the uranium had exposed the photographs without any sunlight at all, and something was radiating from that metal continuously, in complete darkness, with no external energy source. Becquerel called them uranium rays, and moved on to other work, because the greatest discoveries often begin as annoyances that refuse to be ignored. But I could not move on, and this phenomenon captured my attention completely, not because of the rays themselves, but because of a question no one else seemed to be asking. Where was this energy coming from? Consider what Becquerel had observed. A substance sitting in darkness with no light, no heat source, no chemical reaction occurring, and yet it was continuously emitting something. Energy was pouring out of this material day after day with no apparent source, and this should have been impossible. The first law of thermodynamics tells us energy cannot be created from nothing. Yet here was uranium radiating as if from an inexhaustible supply. For 50 years, fraudsters had been selling perpetual motion machines to gullible investors. And now sitting in a laboratory was a substance that appeared to be exactly that, a genuine perpetual engine mocking the fundamental laws of physics. Respectable science had begun to resemble a confidence trick. I chose this phenomenon for my doctoral research at the Sorbonne, and my husband Pierre and I set up our equipment in an old dissecting room at the École de Physique et de Chimie in Paris, a space so unsuitable that the university would not officially recognize it as a laboratory. The shed leaked when it rained and had almost no ventilation, but it was a space to work, and that was all I required. Pierre and his brother Jacques had designed a piezoelectric electrometer sensitive enough to measure the faintest electrical currents, and using this instrument, I began my systematic investigation. I gave this phenomenon a name, radioactivity, from the Latin word for ray, and I set out to discover whether it was unique to uranium or something more universal. Every form of uranium I could obtain went through my tests, including metal, oxide, salt, solutions, and compounds, heated and frozen and combined with acids. What I discovered was something no one expected. The radiation of uranium compounds depends only on the quantity of uranium present, not on whether the uranium is combined with other elements. Not on temperature, not on light or darkness, not on the chemical state of the uranium at all. Absorb what that means for a moment. If radiation were a chemical property arising from how atoms bonded with each other and from molecular interactions, then it should change when the chemical environment changed. Dissolving a substance, heating it, and combining it with acids transforms its chemical properties, but this radiation remained constant regardless of conditions. Only one conclusion was possible. and it was that the radiation was not coming from molecules but from the atom itself. Radioactivity is an atomic property of matter, a characteristic of the element uranium as basic as its weight or color. This was the first crack in an edifice that had stood for millennia, because the atom, supposedly indivisible, was doing something, and something was happening inside. What I found next widened that crack into an abyss. Every element I could obtain went through my measurements with painstaking precision, and most showed nothing, while thorium showed activity similar to uranium. Then I turned my attention to certain uranium ores called pitchblende and chalcolite, and the results made no sense. These minerals were 4 times more radioactive than pure uranium, which raised an impossible question. How could an ore containing uranium be more active than the pure element itself? The situation resembled discovering an alloy stronger than both its component metals combined, unless there was something else in those minerals, something far more radioactive than uranium, something unknown. My thinking at that time was that the greater activity of the natural minerals might be determined by a small quantity of a highly radioactive material different from uranium, thorium, and the elements known at present. If this was the case, I might be able to extract this substance from the mineral by the ordinary methods of chemical analysis. Pierre abandoned his own research on crystals to join me in this search, and we hoped the proportion of the new element might reach several %, but in reality it was far lower. Our persistence created something unprecedented, a method of searching for new elements based not on their weight or color or chemical reactions, but on their radioactivity considered as an atomic property. July of 1898 brought the announcement of a new element, which I named polonium after my native Poland, a country that did not exist on official maps, partitioned and occupied, but which existed in my heart. By December, we could confirm there was something else in that ore, something even more active, another new element hundreds of times more radioactive than uranium that we called radium, from the Latin word for ray. Confirming its existence and isolating it were vastly different challenges, and the proportion of radium in pitchblende was far less than we had imagined. To obtain a visible quantity, we would need to process a staggering amount of ore. 8 tons of pitchblende residue came from the St. Joachimsthal mines in Bohemia, the waste product after uranium extraction that the mines gave us for the cost of transport. Some days I spent mixing a boiling mass with a heavy iron rod nearly as large as myself, and I would be broken with fatigue at the day's end. While other days the work would be most minute and delicate fractional crystallization in the effort to concentrate the radium. A working gold mine would process less raw material than we did, yet even the poorest vein would yield far more product than our efforts. A gold miner would have wept at the ratio, but we were not mining for what could be weighed, because we were hunting for what could only be measured. Nearly 4 years passed before I held 1/10 of a gram of pure radium chloride in my hands. 1/10 of a gram extracted from 8 tons of ore was enough to prove that radium was truly a new element with an atomic weight of 226.45, enough to measure its properties, and enough to confront us with a truth that would shake physics to its core. Radium glowed in the dark with a soft, mysterious blue-green luminescence that persisted hour after hour and day after day with no external source of energy. Pierre would carry a small tube of radium salts in his vest pocket to demonstrate this glow at lectures, and Henri Becquerel did the same. Then came to us delighted and annoyed in equal measure because the radium had burned him through his clothing. His words were that he loved it but owed it a grudge. Radium was also warm, always warmer than its surroundings, and we measured this heat with precision. A sample of radium continuously gave off enough heat to melt its own weight in ice every hour, and this went on hour after hour, day after day. The question of where this energy was coming from seemed to violate everything we knew about the conservation of energy. I wrestled with this dilemma in my writings, noting that uranium exhibits no appreciable change of state and no visible chemical transformation, remaining, or so it seems, identical with itself, while the source of energy which it emits remains undetectable. Therein lies the interest of the phenomenon, and there appears to be a disagreement with the laws of science which, until now, have been considered general. Some suggested the energy might come from outside, that all of space was traversed by some unknown radiation that radioactive elements could absorb, but I recognized this for what it was. Any exception to the conservation of energy can be evaded by invoking unknown energy from space, but to adopt such an explanation without identifying the source amounts to the same thing as admitting we do not understand. That was an evasion, not an explanation. Another possibility existed, one so radical that it threatened to overturn not just physics, but chemistry itself. What if the energy was coming from inside the atom? And what if the atom was not stable at all, but was transforming and destroying itself and releasing the energy that had held it together? The materialistic theory of radioactivity explains the phenomena we observe, but if we adopt this theory, we have to admit that radioactive matter is not in an ordinary chemical state. The atoms do not constitute a stable arrangement because particles smaller than the atom are being emitted, and the atoms, indivisible from the chemical point of view, are here divisible. Atoms are destroying themselves by ejecting pieces of themselves into space and becoming something different from what they were. In 1903, I defended my doctoral thesis on radioactive substances, and the examination committee at the Sorbonne declared it the greatest contribution to science of any thesis they had evaluated. 6 months later, I stood in Stockholm, sharing the Nobel Prize in Physics with Pierre and Becquerel as the first woman ever to receive that honor, and 8 years after that, I would stand in Stockholm again, this time alone, receiving the Nobel Prize in Chemistry. No other person in history has been awarded Nobel Prizes in 2 different sciences. Between those 2 ceremonies, I lost the person who had made this work possible. In 1906, Pierre was struck by a horse-drawn wagon crossing a Paris street after rain had made the pavement slick, and he fell beneath the wheels. The work continued, but our partnership did not, and what I discovered about irreversibility after that day, I discovered alone. Ernest Rutherford and Frederick Soddy worked with radium samples from our laboratory and demonstrated the full picture of what we had glimpsed. Radioactive atoms spontaneously transform into other elements, and a radium atom does not remain radium forever. When it emits what Rutherford called an alpha particle, which is a helium nucleus, it becomes something else entirely, and that something else is radon, a gas. Radon itself is unstable and transforms again, emitting more radiation and becoming polonium, and the chain continues with element changing to element until finally a stable atom of lead is formed. This is transmutation, the alchemist's dream achieved not through incantations and crucibles, but through the patient unraveling of matter's deepest secrets. The alchemists sought to transform lead into gold through heat and chemistry and failed because they were working at the wrong scale, since chemical reactions cannot touch the atom's core. But nature accomplishes transmutation continuously and silently inside every radioactive substance in the universe. And here is what separates this from every other change you have ever witnessed. This transformation is one way, absolute and irreversible. Other changes, you know, work differently. Ice melts into water, and water freezes back into ice. A chemical reaction can often be reversed with the right conditions, and even mountains can be rebuilt by the slow processes of geology. But when a radium atom transforms into radon, it is gone, and there is no reaction, no force, no intervention that can turn that radon back into radium. The transformation has released energy that cannot be recaptured, and the information that made that atom radium has been lost to the universe forever. This is not merely a property of exotic elements, because this is why time has a direction. If atoms could undecay and lead could spontaneously become uranium, there would be no arrow of time, and past and future would be interchangeable. The irreversibility I discovered is not just a feature of certain elements, but the reason before and after have meaning, and it is why you cannot unscramble an egg, unbake a cake, or unlive a life. Radioactive decay and compound interest follow the same equation with opposite signs, one building wealth and one dismantling matter, and nature understood exponentials long before bankers did. Each radioactive element has what we call a half-life, a characteristic time in which half of any sample will transform. Radium's half-life is about 1,600 years. Uranium-238 is 4.5 billion years, and polonium-210. The element I could never isolate in pure form has a half-life of just 138 days, which meant it was disappearing even as I performed my meticulous crystallization. Whether the process takes seconds or eons, the direction is always the same, toward transformation, toward release, toward a state that cannot be undone. What I will show you now reveals what this irreversibility truly means. Each type of radioactive atom has its characteristic half-life, and this half-life cannot be changed by heating, by freezing, by crushing the material under immense pressure, by bombarding it with other particles, by any chemical reaction we can devise, or by the passage of time, or the violence of circumstance. Consider how extraordinary that is. Almost everything in the physical world can be influenced by external conditions, because heating a metal expands it, cooling a gas condenses it, and applying pressure changes a substance's properties. But radioactive decay proceeds at exactly the same rate, whether the atom is at the temperature of the sun or the cold of interstellar space. This tells us something about the nature of the transformation. It is not triggered by anything external, but comes from within the atom itself, spontaneous in the deepest sense, arising from the basic nature of the atom's existence, rather than from any cause we can identify or influence. We are accustomed to asking why things happen. Why did the glass break? Because it was dropped. Why did the fire go out? Because it ran out of fuel. But asking why a particular radium atom decayed at this precise moment rather than a moment earlier or later yields no answer, because the transformation is not determined by any prior cause. As far as we can tell, it is genuinely random, and we can say that half the atoms in a sample will decay within 1,600 years, but we cannot say which atoms or when any individual atom will transform. This randomness is not a limitation of our knowledge, and it is not that we simply have not found the hidden mechanism yet. The randomness appears to be fundamental to the nature of reality itself, because matter does not behave like clockwork with predictable gears. At the deepest level, it behaves like something making choices we cannot predict. What I observed in my laboratory would later be called quantum indeterminacy, the same principle that would drive Einstein to protest that God does not play dice with the universe, but God, it appears, does exactly that. What does it mean that matter is in continual transformation, that stability is an illusion, and that change is both spontaneous and irreversible? First, consider permanence. We build monuments from stone because we believe stone endures, and we store our most precious documents in vaults, trusting that the material will remain what it is. But every piece of matter, no matter how solid it appears, contains atoms that are slowly and invisibly transforming. Nothing is eternal, not even gold, that symbol of permanence that drove alchemists to madness, because gold contains trace isotopes decaying at this moment. The difference is only one of time scale, with some transformations so slow that half-lives of billions of years make them appear stable on human scales, while others are so fast that the substance barely exists before it is gone, but the direction is always the same. Second, consider energy. The discovery that atoms contain vast stores of energy released slowly through radioactive decay transformed our understanding of what powers the universe. The sun does not burn like a fire, but transforms matter at the atomic level, releasing energy locked inside since the cosmos began. Within decades of my research, this understanding led to treatments that could target cancer cells with radiation, since radium destroys diseased tissue faster than healthy tissue, a property we recognized even before we fully understood its source. These discoveries led to power plants that could light entire cities from the energy within the atom, and they led to weapons that could destroy those cities in a flash of light. My daughter Irene continued this work with her husband, Frédéric Joliot, and they would win their own Nobel Prize for discovering artificial radioactivity and proving that transmutation could be induced rather than merely observed. The science I helped birth grew into something I could not have imagined. Third, consider time itself. Radioactive decay provides us with clocks that cannot be reset, and because the half-life of an element is unchangeable, we can use radioactive isotopes to measure the age of objects with extraordinary precision. The age of rocks, of fossils, of ancient human artifacts, and even the age of the Earth itself have all been determined through radioactive signatures that cannot be forged or erased, making them nature's original immutable ledger. The Earth is approximately 4.5 billion years old, a number established by measuring uranium decay. Before radioactivity was understood, scientists had no reliable way to date our planet, and estimates ranged from thousands to hundreds of millions of years. Radioactive timekeeping transformed our understanding of cosmic and geological history. Return with me to that piece of uranium I asked you to imagine at the beginning. You see it sitting there, apparently unchanged, but now you understand what is truly happening. Inside that metal, atoms are transforming, as uranium becomes thorium, which becomes protactinium, then uranium again, but a different isotope, then thorium again, then radium, then radon, then polonium, and then lead. A cascade of transformations unfolds, each one irreversible, each one releasing energy, each one marking the passage of time. That piece of metal is a clock that has been running since before the Earth formed, and it will continue running until every atom of uranium has transformed into lead. Half of it will transform in 4.5 billion years. Then half of what remains will transform in another 4.5 billion, and so on, approaching but never quite reaching zero, which is the mathematical consequence of exponential decay. Nothing you can do will stop this clock, because you cannot speed it up or slow it down, you cannot reset it, and you cannot return the lead to uranium. The transformation is written into the basic nature of the atom, and will proceed as surely as tomorrow follows today. This is what I discovered about irreversible change. Not just that it happens, but that it happens at the most basic level of matter. The atom which we thought was eternal is mortal. The substance which we thought was permanent is temporary. And the stability we perceive is an illusion created by the slowness of the process and the shortness of our lives. My notebooks from those years in the shed remain too radioactive to handle without protection to this day, stored in lead-lined boxes at the Bibliothèque Nationale de France, where researchers must sign liability waivers and wear protective equipment to consult them. My own body absorbed what I studied, and my fingers bore permanent scars from handling radioactive materials. In the end, the radiation that I spent my life investigating destroyed my bone marrow, and I died in 1934 of aplastic anemia, my blood unable to replenish itself, my body transformed by the same forces I had worked so hard to understand. But what of that? Nothing in life is to be feared because it is only to be understood, and the more we understand, the less we fear. I spent my career studying substances that were destroying themselves, and what I found was not despair, but beauty. A scientist in the laboratory is not merely a technician, but also like a child, placed before natural phenomena that impress her like fairy tales. The glow of radium in darkness, the heat that pours endlessly from a tiny sample, and the transmutation of elements that alchemists could only dream of filled me with wonder, even as I understood that they represented matter in the process of its own transformation. We called it a discovery, but perhaps surrender would be more accurate. The atom revealed itself when it was ready, and our persistence merely positioned us to receive the revelation. We are all made of matter, and our atoms too are on their own journeys of transformation, though on time scales so long that we need not fear them. The carbon in our bodies will one day be something else, and the elements forged in dying stars continue their transformations until the stars themselves burn out. This is not tragedy, because this is truth, and there is freedom in accepting what cannot be changed. Stability can only be attained by inactive matter, but nothing is truly inactive. Everything is in motion, in transformation, in becoming. The universe is not a static picture to be observed, but a process to be participated in. That is what I learned from radium, not just that atoms decay, but that decay is creation by another name. The energy released powers the cosmos. The elements created seed, new worlds, and the irreversibility of change is what gives time its direction and meaning its weight. You cannot go back because no one can, but you can go forward, understanding more deeply what you are and what surrounds you. And in that understanding there is beauty, the same beauty that kept me working in that leaking shed, stirring boiling masses with iron rods, crystallizing and recrystallizing, searching for 1/10 of a gram of something that would change everything. The work must be done for itself, for the beauty of science, and then there is always the chance that a scientific discovery may become a benefit for humanity. That is how I approached my research, and that is the truth I hold closest. The unit of radioactivity bears my name now, the Curie, but names fade. What persists is the knowledge, and what endures is the understanding. Matter changes, and time passes, and nothing can be undone. In the face of that truth, we persist, we study, we understand, and we find wonder in the very processes that transform us. That is what radioactivity taught me, not just about atoms, but about everything.